Hi, welcome to this video. In this video, I'm going to talk a little bit about how you apply redox reactions to real-world practical applications in what we call electrochemical cells. So I'm going to talk a little bit about galvanic cells, which are in reality just the same thing as voltaic cells. So they're essentially the same thing. And we'll talk about a little bit about the history here. So galvanism was discovered by a person named Luigi Galvani, who lived in the 1700s, 1737 to 1798. And he worked together actually with his wife, who was named Lucia Galvani, to discover different things about human anatomy and about anatomy in general. But one of his most important discovery was when he connected two different metals to the legs of dead frogs. And what happened is that when he connected two different metals to the legs of dead frogs is that he could basically reanimate them. So the legs actually started to twitch. And for a long time then we thought, and that's what we call galvanism, and what that actually helped us discover was then something about the nature of the nervous system, which is basically an electrical system. He had at the same time at the University of Bologna a friend or a colleague named Alessandro Volta. Volta lived at about, he was a little bit younger. He was born in 1745, lived until 1827. Alessandro realized that it was probably had nothing to do with the frog leg, that the frog leg had nothing to do with it, that it was actually then the two different metals. And so Alessandro Volta is credited then with being the first person to recognize something called the electrochemical series, which is if you have two different metals, they can generate an electrical potential if they are separated by an electrolyte. An electrolyte is just basically an ionic solution. And basically he showed that if you put the same two metals together, then you don't generate any electrical potential, but if you put different metals together, you do generate an electrical potential. And he was then able to organize these in terms of how much electrical potential they have, and so he's accredited with the electrochemical series. He's also credited with making the first battery, so we can take over here the first battery, which we'll talk about in a minute, right? What he also showed, though, which was very important at the time, was that he was able to show that showed that electricity can be generated from static objects, right? And what that means is that they're non-moving. And at the time, this was really important because already at that time, there had been inventions made where you could generate electricity by rotating, right? So there had been experiments with rotations, right, where you generated electricity. And indeed, Benjamin Franklin had also shown that electricity was present in lightning. So there was a lot of experimentation going on at the time with regards to electricity, and Galvani and Alessandro Volta made significant contributions. So much so that Alessandro Volta gives the name to the unit that we use for electrical potential, volt. So his contributions are considered quite significant. So let's look at his voltaic pile, or what we call the volta stack. So here's what he basically did, and he did this with several different metals, but let's give the first one that he did. So what he basically did was he took these plates, metal plates of zinc, and then copper, and then zinc, and then copper again, and he put between them cloth, basically. So this was the electrolyte, what we now call an electrolyte, was basically a salt solution on cloth. And the reason that it's important to talk about this cloth is because there can be no direct contact between the electrodes. Otherwise, if there is, then the electrons will find the path of least resistance, and there will be what we call a short circuit. There will be no overall circuit. And so what happened was that if you connect this, then if you add a connector down here and you add a connector down here, up here, then you will get a minus pole and a plus pole. And in theory, then, if you connect this to each other via some sort of conductor, you get a voltage. One of these combinations is called an element. And we will also learn that it's also now sometimes called a cell. So one thing. So the first battery looked something like this, and this is what we call the volta stack. It's also sometimes called a voltaic pile or a volta pile, because they're piled on top of each other. This voltage then is what we consider then the EMF. So this potential is usually considered then, the voltage is a measurement of the electromotive force. Which is basically the force which is causing these electrons to move. So we have to remember that what we're really talking about here is then electrons, and the electrons are moving through this circuit, right? They're being generated by this combination of metals over here, which some of which are being reduced and some of which are being oxidized, and that generates a force on the electron which allows it to travel through the circuit. So we can write it in terms of then the potential of the electrons being moved. Now, what are they being moved by? Well, they must be getting pushed by something that's giving away electrons. So anything that's giving away electrons is being pushed by then the oxidation process. And if it's being pushed, it's also being pulled because it's creating this sort of circuit. So just because something wants to leave doesn't mean it has anywhere to go. So something has to be pulling it as well. And so this is when you have the reduction process. And if we recall from our oil rig, right, oxidation is loss and reduction is gain. You can kind of put that together with this push-pull process. So EMF then is an important concept that we'll deal with in a later video. Today we're just going to go through these galvanic cells. So if we look then at the galvanic cell, and we'll give an example of this one, except we'll put it a little bit more detail. We'll do a general type first, and then we'll go into one that's very specific. So let's look at the situation that we would have in a generalized voltaic or electrochemical cell. These are also called galvanic cells because they're both sort of attributed to the same process. So here we have then two pieces of metal that have been submerged in an electrolyte. Right? And the electrolyte is then usually an ionic solution. There are some kind of strange exceptions that I'm not going to go into right now, but in some cases they're not ionic, but almost always they are. And then we have this situation where we have metal 1 and we have metal 2. And these two metal pieces are called electrodes. And even if they're not made out of metal, they're still called an electrode. And sometimes we actually have then special kinds of electrochemical cells or batteries that don't actually have a metallic electrode. They can actually have a liquid electrode in some cases, or a gas electrode for that matter. And those are special cases that we deal with a little bit separately. So in order for this to work, as I said earlier, there has to be an oxidation and a reduction. So we're going to just label this arbitrarily. We're going to say that metal 1 is undergoing oxidation. And this is then the loss of electrons. So if it's losing electrons, then the electrons are going away. And they're leaving this electrode. And if that's going to be the case, they have to be going somewhere, because in redox reactions or oxidation reduction reactions, you can't have electrons flying off into space. If you are in the outer atmosphere and you're being bombarded by radiation from the sun, you can be going off into space, but not in normal situations. So if this is the situation, then the electrons are flowing from this metal to this metal, then this metal, if this one is oxidizing, then this one must be undergoing reduction, which means that it's gaining electrons. But in order for this one to lose electrons, this metal must be undergoing some sort of change. So it must be turning into an ion itself. So this electrode is being oxidized but if we were to observe it, we would observe that it was actually being corroded. So it's corroding. And in normal language, we might say it was rusting or dissolving. And it's sort of slowly dissolving into the solution. If the electrons are traveling through here, then, because this thing is being slowly corroded or broken down, the electrons travel over here and are deposited on the surface of this electrode. So there's little electrons here. Of course, you can't see these electrons, but they are on the surface. And so these little electrons are forming on the surface of this electrode, and they're going to attract some other material from the electrolyte. So if this is, let's say that this is metal 2 and this is metal 1. So what's basically happening is that you have, this one is turning from, these are being reduced. So they're being reduced from the solution by gaining electrons at the surface. Now, it's really important that right from the beginning, this is a little bit more complicated than it would seem. Even though this one is corroding and it's turning into the ion of this particular metal, this material here may or may not be the same as this. Because the electrons are being deposited on this electrode, you could be attracting any positive ion. So this positive ion, whatever it is, we can let's call it like, I don't know, let's find it material X. It could easily just as much be X that's being reduced. So if we look at the overall reactions, then we could say that here M1 is turning into M++ electrons. And at the other side we have then M2+ gaining electrons and becoming M2. And this is a purely theoretical situation. So this is a general kind, and if this is going on long enough, then, and if it happens, if it's successful, then it's generating a voltage potential between the two electrodes. And this will continue until this electrode is completely corroded and basically gone, and then it becomes depleted. And once it's depleted, then no more electrons can be given off, and the battery is dead. If it's a special kind of battery, like an accumulator, it can be recharged. But those are very special situations. Let's look at one specific type so that we can understand this a little bit more in detail. So in this case, I'm going to draw something called a Daniell cell, although many people before him actually did this experiment. It's just that he did a very, very special case here. So what he did was he learned that you could measure the electromotive force between two electrodes by separating them into two compartments. And these compartments are called, sorry about that, half cells. And so if you submerge then an electrode in one of these half cells, let's say that this is zinc in this case, and we submerge another metal on the other side. Remember, it has to be two different metals, otherwise there's no cell. And put copper here. What Daniel realized, and he was a French chemist, maybe physicist, that you can get a very accurate measurement of the exact electropotential between these two by creating what he called then a standard electrochemical cell, or what came to be known as a standard electrochemical cell. So in this particular side, he put in, or what we do is we add exactly 1 mole per liter of zinc 2 plus. And this is usually in the form of then zinc sulfate. And on the other side, we have exactly 1 mole of copper 2 plus ions. And this comes in the form of copper sulfate. And we can put square brackets around to indicate that there's a solution. If you connect these two to each other, you get a voltage potential. But it only lasts for a moment. Then it immediately stops. And the reason for this is because what has happened is that the zinc has gone from being zinc and turned into zinc 2 plus 2 electrons. So we have to think about this. This is what's going on. We're thinking this now, right? Bloop, bloop, bloop. But if that's occurring then, and the electrons disappear up here, so we have now 2 electrons moving up from here. What we're putting into solution is we're making this solution more and more and more plus, because we're adding more and more zinc 2 plus to it. But it can't become more plus because it has to maintain neutrality. So the voltage potential will go for a moment and then it'll stop because there will be an imbalance in the the distribution of charges in this solution. At the same time, in this, we have to think that in this one, copper 2 plus 2 electrons is turning into copper. And so copper is accumulating on this electrode here. So zinc is dissolving and copper is accumulating. But it can't go anywhere because as you remove the copper, you're removing positive charges. So this solution is becoming more and more negative. So the solution to this problem, when you want to isolate the two processes, as you do in a standard electrochemical cell, is you have to connect the two with some sort of salt bridge. And this is called a salt bridge. Now in a normal battery, this can actually literally just be like a piece of paper. And in Volta's example, it was pieces of cloth. But what this allows for then, and if you literally take it for what it is, then you say that it is NaCl. We can literally say it's salt bridge. Now what happens is then if this is becoming more and more positive, then ions from the salt bridge move in to equalize that charge. So ions, and in this case it's going to be Cl minus ions, move into here to balance out the charge difference due to the oxidation of zinc. In the other half cell, remember this is a half cell, in the other half cell we have the other situation. This one is becoming more and more negative because we're removing the copper 2+ ions. So because it's becoming more and more negative, plus ions move out of the salt bridge in order to equalize the charge. So sodium ions flow from here into this. If there's a successful transfer of ions from the salt bridge, then this battery will continue to work, or this cell will continue to work. And because we have a standard here, it will generate then exactly the voltage potential that you would expect. There's no difference in the potential on there's no difference in the concentrations of ions on either side, and so it will generate what we call a standard electrical potential, which will be the subject of our next video. So the next video will be standard electrical potentials. Just so you know, I'm not going to talk about this time. But before we leave this then, it's important that we recognize what's going on with this. If zinc is turning into zinc plus, then it is undergoing oxidation. So we have oxidation, right? Electron loss. And copper is undergoing reduction. And sometimes we call this the oxidation half cell. And this is the reduction half cell. And together they make a electrochemical cell. If you put many of these together, you get what we call a battery. Okay, that is the end of this video. I hope you enjoyed it, and I hope it was a good explanation.